section L, that force, call it F of B if you want to, is the current I, which we have there. We get the length L, which is this length, multiplied by the magnetic field. There is no sign I anywhere because the angles are 90 degrees. And so I find that that force is 300 times 0.1 times 0.2. So that is 30 times 0.2. That is about 6 Newton. 6 Newton is more than the weight of 1 pound. And so it is not so surprising that when I turn this current on, that something all of a sudden pulls that wire down with a weight that is equivalent of a little more than a pound, almost a pound and a half actually. And so it's not so surprising that these supports fell over. So you see that you can turn this quantitatively, provided that you make some simplifying assumptions about the uniformity of the magnetic field and about where the magnetic field is present. Now, I want to talk about the great 802 motor contest. We are about to start on this great 802 motor contest. You got an envelope today, and I'm going to start to tell you slowly about the physics. The goal is ultimately to build a motor. If I have a current loop, here's a current loop. Current comes in at A, and I'll try to make you look at it three-dimensionally, which is not so easy. This is, the current goes out here at D. This is a current loop. Current goes through here, goes through here, goes through here, and returns here. And we have a magnetic field, and we will assume that the magnetic field is constant throughout in this direction. There is a force right here on this wire in the direction I cross B. That force is up. There is a force here on this wire, which is of course down. Magnetic field is in the same direction. The current is in the opposite direction, so the force is down. If this wire has a length A, this wire has a length A, that force, the magnitude of that force, is the current through the wire times the length of the wire times the B field. We just derived that. It is that integral. We just assume that the magnetic field is constant everywhere here. They're at 90-degree angles, so the sine of theta is 1, and so that's the force. What is the force here and what is the force here? Well, it's 0. 0 here, and it is 0 here. Why is that? Because the cross product is 0. No matter how you look at it, you can say dl and b are either in the same direction or in opposite directions. You can also say the drift velocity and b are either in the same or the opposite direction. It's all the same thing. There is no force here, and there is no force here. Because that equation that we had that gives us the magnetic force becomes 0. The sine of that angle is 0. So what's going to happen with this thing? Well, there is a torque on this system. There is no net force, because this force up is the same as this force down. But there is a torque which wants to rotate it in counterclockwise direction. And the magnitude of that torque is, of course, this force, remember from 801, times the perpendicular distance between these two forces. And so the magnitude of that torque is I times AB times B at this moment in time, when the forces are this far apart. Now this is going to rotate, and so as they rotate, these forces come closer, and so the torque will become less. Still, it wants to rotate counterclockwise. And there comes a time, 90 degrees later, that the torque is 0. And I will try to make you see that again in a three-dimensional way. It's not so easy for me. Now this is D. This has become D. The current always leaves at D. I'll try to make you see this three-dimensionally. Goes like this. The current comes in here at A, so we get this, and we get this. Doesn't look so bad. And the magnetic field B has not changed. Uniform B in the same direction. So the current now comes in through A, that has not changed. The only thing is that the loop has rotated 90 degrees. If now I ask you what the forces are, you have to go I cross B. I cross B. If you do I cross B here, I cross B, you get a force which is towards you. Here, you get forces which are in the blackboard. Here you get forces which are up, and here you get forces which are down. At home you will have some time to use your right hand and do the I cross B, and you will see then that indeed all these forces are in the direction that I put them. So now there is again no net force on the system. There was no net force here either, but now there is no torque either. So now the torque has become 0. If we rotate it a little further, it is possible when we start this motor, starts to rotate counterclockwise, comes to this position, torque goes to 0, but it has enough inertia, so it rotates a little further. And now the torque will reverse. And this is something that I leave you alone with. I don't want to make another drawing and convince you that it reverses, but it's easy to see, because take this thing and just flip it over 180 degrees. The magnetic field hasn't changed, but the currents in these two sides have changed direction now, because whatever is D is here and A is here. And so the torque reverses, and so it goes like this, and then it comes back. And that's not much of a motor. Current meters are very frequently used. They are in your cars many more than you think. Your fuel gauge and your temperature of the cooling water are current meters. And the current meter works as follows. We attach to this loop a needle, a handle, and we calibrate it here. And you can read how many amperes are going through this meter. It wants to go counterclockwise. Here we attach a spring, and the spring produces a counter torque, and so the needle will start to deflect but come to a halt. But if you double the current, it will go further. That's the way that a current meter works. And your fuel gauge in your car is a current meter, except that the level of the fuel is somehow converted into an electric signal, and then it's sent through a current meter, and that's what you're reading. And it is, of course, calibrated in terms of how much fuel you have. And your temperature gauge is calibrated in terms of degrees, whatever, Fahrenheit or whatever. So